Well, multifractal processes have been introduced in turbulence. So turbulence is the study of fluids with a very high velocity. When I mean high is that I mean that the speed of the fluid is much more important than the viscosity forces. So they have been introduced to reproduce intermittency phenomena. So what I want you to understand is that multifractal processes are connected with intermittency. So what is intermittency? Intermittency is some kind of strong activity clustering of your process. So for instance, you have to look at well, you can assume you have a process. If you observe such a curve for g increments of your process, so there is no periodicity. It's just if you observe some areas with a strong activity, it is intermittent, and you have some areas with very small activities. For instance, a process that is not intermittent is the Brownian motion. If you plot the increments, you observe something like that. This is a white noise. If you plot a fractional Brownian motion, you observe something that looks like that. You have examples in the notes where I plotted a fractional Brownian motion, multifractal processes, and well, very roughly, you can observe for your process something like that. So I plot xt and say yt here. It is very rough, but assume you can compute something like the expectation. It is a random process, so you can compute the expectation of your process at some power q. And when t is small, you observe that it is like a constant times the power of t. And assume that this power is not linear in q. Then you say that your process is multifractal. This holds when t is small. And for this process, should be something like that. It is likely to behave with a linear power law spectrum. This is linear. This is non-linear. When it is non-linear, you observe intermittency, some kind of strong activity clustering, and when it is linear, you should observe something like that. This is behind this idea is the multifractal formalism that tells you that for processes like that, the strength of your increments is always the same, instead of here, where some points are bigger than other points. So this is the ideas of my course. I want to introduce a simple subclass of multifractal processes. And the simple class is called Gaussian multiplicative chaos. So the first part of my lecture will be to prove a technical lemma that is very nice and of independent interest about convexity inequalities for Gaussian random variables. Then I will construct, I will tell you how Gaussian multiplicative chaos works. And then I will give you examples. And the final example I want to construct is the quantum measure that has been introduced in the Liouville field theory by Duplantier and Sheffield. And I want to prove you that this is a simple application of Gaussian multiplicative chaos. Okay? So So just a remark. It may be surprising to find multifractal processes in finance. So in my introduction, I haven't detailed why it occurs, but I just gave some empirical facts that show you that in finance, when you observe stock markets, you have this kind of curves for the log price of the stocks. This is surprising, but so you can apply mathematical techniques of finance of turbulence in finance. This is well, I'm looking for how do you okay. Well, so my first point is my first point is will be to prove you convexity inequalities. For Gaussian random variables. Well, so this is a bit abrupt, but this is the main technical lemma of the. It is not very complicated, and it is the main technical lemma of the theory. And once you have this lemma, you can do everything you want in multiplicative chaos theory. So, so I was told to be careful with the background. So I just remind you a few points about Gaussian processes. So it is very basic. So you all know that a Gaussian process. You know that a Gaussian process is a process which has all its finite dimensional distribution Gaussian. It's okay with that? Okay. What do we want to say? So, given a Gaussian process, so this is just a reminder. Given a Gaussian process, you can define the covariation kernel. So it is called this is also for my notations. When you are given a Gaussian process, say X, this will be the covariance kernel. So this is just the covariance between XU and XV. And you know that when the process X is stationary, you know that K of X only depends on the difference U minus V. Are you okay with that? This is just a function of the difference, and the function G is of positive definite type. Okay, you know. Okay, J is. I don't know if it is the classic terminology. J is of positive type. And so as soon as you have a function of positive type, say G, there exists a Gaussian process, a stationary Gaussian process X, with the given covariance kernel. Okay. So good. So we can start the main lemma. I think I can write here. So I will give you a lemma, and then there are many applications that are of independent interest. So you take two Gaussian vectors. So let's. Two centered. Everything, when each time I consider a Gaussian vector or a Gaussian process, I assume it is centered, okay? And if I need, I will subtract the mean, okay? Everything is always centered. Two centered independent Gaussian vectors. Take a family of positive numbers, so just in R plus, and take phi well, say phi has to be take it smooth to a single sample and with polynomial growth, but I don't write the assumption because you just have to make what I consider exists. So yes, define phi t is just the expectation of phi applied to a sum I haven't defined z yet, so I will do it. So here zy is a Gaussian process, and it is defined by so what is it? This is just an interpolation between x and y. Okay. So if I manage to control this quantity with respect to t, I'll have a comparison principle between the value in t equal 0. This is just ye, and the value at 1, and this is xi. Okay. So I want to have a formula for the derivative of this expression, and then I'll have a corollary for. So just notice that the expectation here because they are independent and centered, this is just t okay. So the conclusion of the lemma is an expression for the derivative of phi. times an expectation, and you have this may look complicated, but conclusions are very simple. With Wn of t is a sum well, assume you can prove that. We'll do the proof thereafter. Assume you can prove that. So you see that in your expression you have so you have the p's and they are positive. You have this difference that you can make positive. For instance, when the covariance kernel of y is bigger than x. And then you have this expression here. This is an exponential, so this is positive. And here you have the second order derivative of phi. So, for instance, if you want to make it positive, you just have to take phi convex. Okay. So you see that the first obvious corollary is when you make everything, you want to have all the things positive. Okay? So there are many very nice corollaries. So assume phi is convex. And say assume that this quantity is always bigger than this one. Let's say positive. So when you have phi convex and this comparison inequality for the covariance kernel, you have, so the derivative is positive, and if the derivative is positive, you see that phi of 0 is less than phi of 1. Okay? So phi of 0, it's just so the expectation with y inside. Are you okay with that? So you see, well, there is an obvious generalization. Instead of taking a discrete sum, you can think about integral and Gaussian processes. So if you have phi convex, x and y, two Gaussian processes. So with the index set in RG. So instead of discrete sum, you can consider integrals. So this is just what I want to write. So the expectation of a convex function so you can compare these quantities, provided you have a comparison between the covariance kernels. Okay? And so take care. So mu is just a positive radon measure. So phi convex, two Gaussian processes, you have mu positive radon, and the covariance kernel of X must be bigger than the covariance kernel of Y. So when you look at a convex function, you see that the bigger the covariance kernel is, the bigger this observable are. Okay, and this measure, this is very interesting because these quantities here can be understood as a Gibbs measure. It's not far from being Gibbs measure, and these convexity inequalities have recently been rediscovered in the context of random polymers. I cannot remember the authors, but they have broken many conjectures about polymers with these simple inequalities. Okay, so this is just what I want to prove, and this is what I will use thereafter. Okay. Is that clear? Or no? Do you have questions about that? So, are you okay with my conclusions? So assume that if this is true, you have that. Are you okay with that, or okay? So you just have to prove. So this as the first guy who proved this inequality was Talagrand in a simpler form, and it has been improved to this form by Jean-Pierre Kahn in the 80s. So this is a rather old inequality. Okay. So you just have to differentiate the function here. So so you just compute. Well, this is not complicated. You just have to be careful when you differentiate it. So I will try to be careful. So you differentiate inside the expectation, and you should have the expectation. There is a sum. You have the derivatives of this function. So you have ye. This is the derivatives of z. You differentiate the expectation of the square. You have this is just the expectation of x minus the expectation of y to the square. So square. There is a big. Then you have the exponential. And then you have the derivatives of phi. Okay. Phi of the sum, right? Yes, and so then you use the integration by parts formula for Gaussian random variables. So I want to isolate this term, so I just rewrite it to be clear. ye exponential I just keep this term and I put this term apart. Okay, I develop the term here, and so you have minus 1 over half sum over e time this quantity. I forgot the P. So you have P exponential okay. So you have two quantities. So here you see that you have this is well. You have to use the integration by parts formula for Gaussian random variables, because you have a Gaussian variable times a functional of a Gaussian random variable. So I remind you of a classical lemma. So take this is just a Gaussian vector. Well, center up, okay, as usually centered. And so F and F. Well, smooth enough, okay? Smooth.
May I ask you a stupid question?
Yes. Sorry?
May I ask you a stupid question because I'm absolutely lost? Is X and Y, are they processes or just variables?
Here in my lemma, they are just variables.
Just Gaussian.
Gaussian. X is in R, and Y is just d-dimensional Gaussian vectors. And the couple is Gaussian. Okay? There is no stupid question. Ask whatever you want. And so you have this. So this is called the integration by parts formula. So when you compute these quantities, it is just this is a vector, okay? This is a d-dimensional vector, and you compute the inner product with the expectation of the gradient of f. So, okay? Do you know this formula? So this is very nice for Gaussian random variables because you can get rid of all these expressions very easily. So.
So what does the idea of x, y?
Sorry, D?
That's some sort of a vector, yes? Ah, that's a scalar product.
Yes, this is in RG.
No, I mean first GA is a vector and
the second, this is a gradient. So f is defined on RG. This is a vector in RG, and you compute.
The right side of the definition stands a scalar product.
Yes, this is a scalar product. Okay. Yes. I don't know what is the notation for scalar product, but this is what I mean. Okay. Okay. This is a scalar product. Okay. If you want, I'll have a word about the proof here in a few minutes. I just want to finish here the proof. Okay. So.
So may I ask you one more stupid question?
Yes, you can.
In that lemma, the situation is as follows, as I understand. We take two random points from two different Gaussian distributions with
Yes.
different integration matrices and with a centered into zero.
Yeah.
Then we make an interpolation.
Yeah.
And we just differentiate by this t.
Yeah.
So these two points are not the processes too. They also are just the variables.
The
Just
two.
the vectors.
I don't understand. You mean zy, right? You're asking me if zy is.
I ask you first about xy and yy,
Yeah.
then about zy.
So
Xy is just a point.
it's just a point
Random point
in RG.
in RG.
Okay.
The yy is also a random point in RG, but
Sorry. You are right. Xy is a point in R, and x is a Gaussian vector in RG. You are right. Xy is in R. X is in RG, and x is a Gaussian vector. The components of which are the xy. Okay.
then we interpolate
Yes.
just some deterministic function.
Yes. We make a deterministic interpolation with a square root. This is because of the.
Interpolation, but this
Yes.
through the interpolation.
Yes. Yes. The interpolation is with square root. Okay. This is not. this is not the square root is not a random decision. This is because the yes, because this is the Gaussian scaling is connected with the square. So I choose the square root because we deal with Gaussian processes. Okay. So then you will see here that this is the correct function to choose to make this term disappear. Otherwise, you don't have you have to face with this term. You will see in the proof that everything disappears. To the final expression I gave you that I just erased. Okay. So I just make the integration by parts, and the proof is finished. So if you have further questions, don't hesitate. Okay. So. So you see, so I have this expression here. This is my x here. Okay, this term is my x, and phi of y is the expression that I have here. Okay, so I do the integration by parts. So I have a sum over y, and then I have to compute this vector. Okay, I have to compute this vector. This vector, this is just the covariance of the vector here and each component of the vector z. Okay, so I have a sum over j. Because the scalar project is a sum, okay? So I sum here, this is, you can write it like that, sum of j, okay? So this is what I do. So I have to compute the correlation here, the covariance here. So with the corresponding component of y, I mean here this is z. Well, this is so the j's component of z is just the square root of t xj minus square root times yj. Okay? And then I've written this term. I just have to compute the expression here. So I have to differentiate here with respect to j. So you see that here you have a function of z, and here you have just a function of the zy. So when you have to consider the case when j is equal to y and when it is not equal. Okay. So here I differentiate with respect to j. So I have exponential of dy of t I differentiate here with respect to j. Okay, so I have exponential of zj of t, and I have the second order derivative of phi with respect to the same sum. Okay, This is when I differentiate here with respect to j. And then I have to differentiate here with respect to j, and the only case of interest is when y is equal to j, okay? So, well, maybe I complicate the thing, but this is just a function of RG. You compute the different the derivative, and so this is just very simple, and maybe I am not clear. Okay, I can grant you that, but you just have your sum. So this is the same expression here, but I just have j equal to y, so I have times this quantity with a y instead of j. Yes, and so you have this quantity, and then this term that you must not forget, right? So observe that this term, this is just a minus this term, okay? Because when you compute here, minus the same thing. Well, remind that x and y are centered and independent. So you just have the square root disappear. You just have the variance of x minus the variance of y. Okay. So this term here and this term here cancels. Okay. Yeah, I forgot the P. So, and if you look at the expression, the same argument tells you that here, the expectation here is just the expectation of x, y, x, j minus the expectation of y, I, y, j. Okay. This is just okay. So this is the formula I gave you. So do you have questions or comments? So from the pedagogical point of view, maybe I try to explain, but maybe you should take your pen and do the proof by yourself. You see that you just have to differentiate. Well, the only difficulty is to differentiate this function without mistakes. Okay.
Can you say once more where this second term comes from?
The second term, this one. Okay, because when you do the integration by parts here, you have to differentiate with respect to the y's variable this function. So this function, this is a product. You can differentiate here, and then you have to add the derivatives here with respect to xy. Okay, and when you differentiate with respect to xy, you just have the second term. Okay, you see this whole guy as a function of z. Okay. Is that clear? Or? So do you know how you prove the integration by parts formula? No? Okay. We can do that. This is very simple because you just have to compute Laplace transforms. Okay. You can do the proof with the Laplace transform and then. So, for instance, you compute. I just do the proof of the lemma. You compute so remind that x is in R, so this is in R, this is in R, this is in Rg, because the y is in Rg. This is just the Laplace transform. Okay. So you want to make appear x here, okay? So how can you do that? You can differentiate with respect to lambda. You can differentiate this expression with respect to lambda. So first you have to compute here the Laplace transform of a Gaussian random variable. This is just so x squared plus what? No, sorry. So you have an inner product. So you have mu variance of y, mu. Okay. This is a vector in Rg, so its covariance is a matrix, and I compute the matrix at the vector mu. Okay. So so this is just the Laplace transform. You differentiate with respect to lambda. You obtain x plus mu dot y. So here you differentiate it and you get lambda expectation of x squared plus and here you have the exponential of the same thing, okay? Yes, so take lambda is equal to 0, and you get the expectation of x exponential of mu dot y, okay, is equal to so because I go step by step. So you get mu exponential of this quantity with lambda equal to 0. Okay, so I just have 1 over half mu Are you okay with that? And this quantity here, this is just the Laplace transform of y. Are you okay? You can say yes or no. Yes? No? Do you agree that this is just the exponential here? This is just the Laplace transform of nu dot y. Are you okay with the? Okay, so okay. So this is the formula you want. This is just x fy is equal to dot the expectation of this is the formula you want, but instead of general f, you just have f which is an exponential, right? Okay, and with density argument, you conclude the proof. Okay, because this is linear in f. Okay, this is with f is equal to the exponential of mu x. Okay. You mean, I don't understand the question. You say, well, I have proved the formula for f is equal to exponential, right? And then this is linear in f, in both sides, okay? So you can say this is true for linear combination of exponential, and then for okay. So this is a simple proof. This integration by parts formula is also true for Levy processes or infinitely divisible random variables. You do the same proof, and you recover your integration by parts formula. But to obtain, to deduce this kind of inequalities, this is an open question. Okay, so I don't say that this is impossible. I just say that this is an open question to know which kind of Levy processes can produce this kind of inequalities. Okay. So well, from these inequalities, you can also deduce comparison inequalities. Instead of having integrals, you can consider supremum or minimum of Gaussian processes. And I won't use it in my lecture, so I don't do the proof. But you have these inequalities in my lecture notes, and this is very striking, because you have comparison inequalities for Gaussian processes as soon as you can compare their covariance kernels. Okay. So let's talk about Gaussian multiplicative chaos now. Do you have questions about so this? I will often use this inequality for almost all the proof in my lecture. So second part. So before yeah, yes. Sorry?
The last corollary, above the maximal to Gaussian,
Yeah.
is usually attributed to Следите.
To
It's a classical inequality published second half of the 50s.
yes. Concerning the former inequality of Talagrand can give you the suprema. This is
Yeah, it's not true, but this inequality was known much earlier.
yeah, yes, it's possible.
Used later by Surakov, Pyramid, Dad.
Yeah, there are many people who worked on the supremum. You are right. So this is just an easy consequence because my lemma is not very technical. So this is just a very simple application to recover the supremum. So the proof is elementary. You can grant me the. Okay. So before starting with formal definition, I just want to remind you what I want to construct and to give you some kind of introduction. So my purpose is to construct a random measure. And what I want to have is something like that, such that my measure will have a nonlinear power law spectrum. I mean, for instance, I construct a random measure on R. So if I construct my measure, I can compute the measure of a segment. Okay, this is a random variable, and I compute the Q's moment of my random variable. Okay, I have a measure M. I compute the measure of a segment. This is a random variable, and I take the Q's power. And I want that. My purpose is to have such a kind of relation, to say things very roughly. So, I want here to have a T of Q nonlinear in Q. Okay, this is the purpose of what I want to do. So. The simplest situation when you have a random measure, you take well, to have a random measure, you can imagine you integrate with respect to the Lebesgue measure, and you have to choose your density. Okay, say we are at the very beginning of understanding something. Okay, so here. Since you want to have a positive measure, you can always thought that you have an exponential, and you have to find what you put here in the exponential, right? So so nothing is random nothing is random here, okay? So to have something random in the exponential, you put a process, okay? And well, it is very nice if the expectation of your random measure Okay, as a is the Lebesgue measure, for instance. Okay, this is kind of a normalization, right? So you want to have the expectation of m of a is equal to the Lebesgue measure of a, and if you want to have a very simple thing in the exponential, you take x to be the most simple process you have. This is a Gaussian process. Okay. You can take, when you start your construction, you may say, well, I consider the exponential of a Gaussian process. This is very simple, and to be normalized, I just have to subtract this quantity here. Okay. So this is the very simple situation. And you look if you look for such measure at the very beginning, and we try to see if this works. Okay, so say x is a nice Gaussian process. So what do I mean by nice process? Nice, well, let us say continuous covariance kernel. Okay, so let us see how do I have to choose the covariance kernel to have such a property. Okay, so so what happens when I take, so let us assume that I have chosen the measure like that, and let us see what happens when I compute m of the segment 0t. Okay, so you have an expectation. To the q's power, right? So what happens when t becomes small? Because your covariance kernel is continuous, when x, the small x, belongs to the segment 0t, you see that xx should be equal to x 0, okay? So this should be of x0. So we should have something like that when t is small. Okay. Well, this is an approximation. A quick computation, but this can be made rigorous with this inequality. So finally you obtain. So you have the expectation. The q's power you can put it inside the exponential. Okay. So you have qx0 minus q square. Sorry. And times t to power q, right? Times t to power q. So you get, well, you can compute. This is the expectation here. This is just the value of the covariance kernel at 0. Okay, so you just have the exponential of q square over 2 kx of 0 minus okay. But what do you see? you are interested in the power of t. Okay, and here you see that the power of t is linear. Okay, this is the power here. This is obviously linear in Q, and what you want to get is something non-linear. Okay, so this is not enough to construct what you want. Okay, so you cannot. We keep this this kind of construction, but you see that there is something wrong, like in that stuff. And what I want to change is continuous. Here, you see that this approximation here make all the computations valid. So you have to change this approximation here. You have to make it not possible. To make it not possible, you have to assume that it is not continuous at 0. Okay? So we'll have to consider here not a Gaussian process with the covariance kernel k of x, possibly divergent at 0, right? So this is a bit, at first sight, this is a bit surprising, because when you have a covariance kernel that is divergent at 0, this means that you have an infinite variance. Okay? So a Gaussian process with an infinite variance, this is not usual, but you can understand such a process as a random distribution. This is not a problem, okay? But the problem is then to assume that you can understand your process as a random distribution. The difficulty is now to define the exponential of a distribution. Okay? If I ask you how to define the exponential of a distribution in the general case, this is not possible. At least you grant me this is not simple. Okay. So if you follow what I say, just okay, you can construct this random distribution, but then you have to face your exponential of a random distribution, right? So this is what I want to do. And so this is what we will do. We have 5 minutes left, so let us begin. So well, I can tell you in a few words what will be the strategy. So assume k of x is your covariance kernel. And well, so you cannot define this object. So what you can do, you say, well, okay, it's divergent at 0. What I want to do is to cut the divergence, construct then an approximate random measure, and take the limit. Okay. So, but you have to understand how you will take the limit. Okay. So what we'll do will be the following thing. Assume that your covariance kernel can be written as a sum of nice covariance kernels. Okay, and nice, I mean continuous at 0. Okay. Assume that each covariance kernel is the covariance kernel of a family of is the covariance kernel of a Gaussian process Xn, and all the Xn's are independent. Okay. So if this is possible, if you can write your k of x as this sum, you will say, well, M will be surely the limit of something, of a measure that looks like that. Instead of having the exponential of x, you will put the sum over the n first processes, right? So you say that should be the limit of something like that. Minus okay, so you want to pass to the limit as n goes to infinity. So why do this measure converge? Well, actually, this is very simple because since all your Gaussian processes are independent, this is the measure mn of A is a martingale, okay? Because when you compute the exponential when you compute the expectation of n plus 1, given the n first processes, so when you compute, here you have the n first processes and the last one. And the last one, because it is the exponential is centered, you get it is very simple to see that you get mn of A. Okay? Are you okay with that? So you see that you have a martingale, and because everything is positive, you have a positive martingale. Okay? And you know that every positive martingale converges almost surely. Okay? So for each set A, you will have an almost sure limit. Okay? And we will see that we can construct with this observation a limiting random measure. Okay? So this will be the strategy of my lecture, and this is what I will explain tomorrow.